think he's going to talk about actual, but only I think a little bit. Most of it will be PCD, I think. Okay. So over to you, Tuhin. I think everybody knows that. So okay. Even our office people know it.
Okay. So, can you hear me? Yeah, I think it's working. All right. So as you'll see in this talk, I have very unusual sense of humor, which often it doesn't work. But anyway. So the first sense of humor is usage of axion in the title. Even though, let me just declare that apart from this slide and the title slide, as far as I remember, there is no axion, okay, in the whole talk. But then you ask me why it is there, and the reason is really this, that if you read papers on archive, particle physics papers on archive, astroparticle physics, even in astrophysics papers, you realize that everybody is talking about axions, okay? From model builders to phenomenologists to constraintologists, right? To all levels of life in these three sides. Basically, it's axion, 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 axion. Okay, so I'm pretty sure many of you came here because there was an axion in the title. So that's the best way to get attention is to put axion in the title. Okay. But let me ask the question is that why did people start thinking about axion? And the answer was, even though today we talk about dark matter, we talk about this and that, everything we think like an axion is a solution. But the main reason in the back of our head, we also know that we talk about axion is because it is supposed to have something to do with the strong CP problem. Okay, and it's supposed to be a very, very good solution. In fact, I still think this is probably one of the best solution to the strong CP problem. But strong CP is a very quirky problem, and I'll come and I'll talk to you. It's subtle, okay. And so, if I have to tell you what strong CP problem is, this literally talks about two different numbers. They seem to be completely uncorrelated with each other's, physics-wise or understanding-wise, and they have to agree to each other to extreme extent. Okay, philosophically that's what the strong CP problem with that. Now, if you are okay with that statement, then you are okay. Then you don't need to do axion at all or strong CP. But anyway, rest of it is as you will do. Most part of my talk I will talk about reviewing the strong CP problem. So if you are an expert in chiral perturbation theory, I'm going to bore the hell out of it, right? But if you are not, then you might understand where the problem originates. And even today, after 30, 40 years of people realizing the problem, the theorists still think about it. And there are very, very different layers of the thought. There are subtleties within subtleties. And to appreciate that, you really need to go to high quantum level to appreciate that part. Okay, and then related to that, I will review what the quark masses are in the standard model. And at the end of the day, I hope that you will be convinced that you really need a new perspective, especially if you don't care about anything else. But let's say you're hell-bent on understanding strong CP. You need to understand what the light quark masses are, and we need a new way to think about that. And the rest of the talk, which hopefully I will talk about the 10-15 minutes or maybe 20 minutes of it. And so again, if you're an expert, it would look like most of the things I'm talking about is something that you already understand. But if you still care about this, just let me know. I'll come and I'll entertain you, for the rest of my days when I'm here. Okay. All right. So let me start. So one of the sector that I talked about is the flavor sector. So what is flavor? There are various people who mean by flavor different things, but here for all part of my talk, flavor would mean generations to me. So we know the quarks, so let's concentrate only on the quarks. So there is an up-down charm, there is a strange top-bottom, okay? And we say that the quarks come in 3 generations, and so that's the flavor, okay? Now, what I mean by fundamental physics gives rise to flavor, what you realize that at the end of the day, when if you are put yourself in God's shoes, that you realize that writing this Yuka coupling, what we write in standard model, it has to be explained, it has to be understood, right? And that's roughly what the flavor physics, the model builders in flavor physics come, is how do you generate these sorts of couplings. So there is an entire branch of physics, which talks about how this flavor, like there are quarks and there are anti-quarks in that language, and then there is a Higgs, apparently not connected to each other. QCD has nothing to do with this. You literally need a different way to generate coupling between them. Okay, so that's the physics of flavor. That's the physics of generations. Okay, now whatever be that physics, the end result of it is two couplings, supposed coupling. So here, as I said, there is a quark doublets. There are quark singlets. There are two quark singlets, up type quark singlet and a down type quark singlet. I'm not using so just to be specific, I'm not using this left-right notation, but you can think of it, this is related to the right-handed quarks, the C, UC and DC, and the Qs are the left-handed quarks, okay? So there are three of those for 3 generation. You see three of those. So YUs and YDs, these are 3x3 general complex matrices. Okay. These are arbitrary so far because we don't know how flavor was generated. But on the other hand, this looks enormous number of things because 3x3, that's 9, the complex 18 number of different parameters times 2, 36, but not all of them are physical. Okay, things are physical because, as you know, in first thing in quantum field theory is that nothing in your Lagrangian is physical, right? So what you write as a field, if you redefine it slightly differently, as long as your, let's say, the S matrix doesn't change, nothing changes. So fields are not physical. Okay, nothing in your Lagrangian is physical. We find a way to connect various things to physical objects at the end of the day, right? So redefinition is a tool which is often used to reduce the number of parameters, and at some point you come and you realize you cannot redefine parameters away. That's the point you realize this must be the ones that I will find in nature, because that's all. Okay, so redefining it and getting rid of the thing, this will take me a few minutes. If you have taken a standard model course, this is again straightforward. What you do, this is a 3x3 matrix, so therefore it's a complex matrix, so it is diagonalizable under a bi-unitary transformation. That means from the left you multiply by an unitary an SU3 element, and the right you have a different SU3 element, and that gives you a diagonal matrix. Okay, so here I write the inverse way, so that two SU3 matrices multiplying a diagonal guy gives you your Y. Now the eigenvalues can have phases. Okay, they are complex. So I just separate it out into an unitary matrix which only has diagonal pieces, and I keep all the phases over here. So Y hat is a diagonal real matrix, 3x3. L and R's are elements of an SU3, and U and D are just 3x3 diagonal matrices with phases. Okay, so that's straightforward. So if I do this, then as I said, I have the freedom to redefine phases, right? Redefine everything, right? So I could redefine my Q times LU. So yeah, as you can see here, if I redefine Q times LU, L dagger, so it multiplies from the left with L and it goes away. Okay, so it looks like if I redefine, I get this particular terms, Q times Y hat times UC. Here I just have to also redefine the phase, the U factors as well. Okay, and so this Lagrangian rather looks straightforward. The first term is only the diagonal pieces, second term is the diagonal pieces, but since Q I already have redefined, I cannot redefine it away anymore. So there is one element of an SU3, another element of SU3, product of that is also an element of an SU3. Okay, so there is an SU3 element. So there is a rotation of 3x3 matrix, but this guy is diagonal. Okay, very good. So far straightforward. So let's just count. Let's say this is an allowed process. So these two kind of operator, it looks, as I said, in quantum field theory, I'm allowed to redefine. So if I redefine, then I find this ginormous number of matrices simplified that way. So y hat, as I said, it has a diagonal and real, only 3 real numbers. Similarly, yd has only 3 real numbers, and then there is one unitary element. Okay, and an unitary element that we can do the exercise, or you can also look at it straightforward to see that it only has 3 angles and 1 phase. Okay, so that looks like a great simplification, but it's not quite right. Okay, the reason it's not quite right is because you see that this is field redefinition away. So when I'm field redefining away in my Lagrangian, if you think of your action in terms of path integral language, there are also measures. Okay, the measure changes under this. Right? So quantum mechanically, it turns out that even though the classical Lagrangian looks L1 is same as L2, but because your measure change, this change element, you can rewrite it as a new contribution to your Lagrangian. Okay? And so it looks like that this Lagrangian L1 is actually not equivalent to L2, but it's actually equivalent to an L2 time a different operator. This particular process where this redefinition or a transformation leaves the Lagrangian invariant but changes the measure, this is what is called anomalies, right? So this particular anomalies that tells you, as I said, that L1, which I started out with many complex stuff, changes to an L2 which has a much simpler structure, much fewer number of elements. But then you get an extra operator where G mu nu is where the gluon fields are, right? This is the F mu nu, but for the SU3 pieces, right? The tildes here, if you remember, if I do FF dual, that looks like an E dotted with B, right? As opposed to E square plus B square, which is the kinetic term, okay? Or this is epsilon mu nu, G mu nu, G rho sigma, right? Epsilon mu nu rho sigma. So anyway, so this is the operator. Okay, so this theta f, as I said, it has something to do with this redefinition. As you saw here, the redefinition involves Q going into L, then D is going into R's, and U is going into R's, and this phases U, this diagonal matrix, that being absorbed into up-quark and down-quark. And this one element, the product of all the 3 phases, which is basically the phase of the determinant, that's what shows up over here, right? But now remember, this whole phase was in YUYD, the original matrix that you started out with, so which is equivalent to this argument of the determinant of the two phases. Okay, so the story is straightforward. The flavor physics, the ultimate short distance physics, gave rise to this particular couplings, which you can work it out and simplify it in a much more simpler description. This looks like a simpler part of the Lagrangian, which is just classical, the same thing, with a smaller number of parameters, with 3 angles, 1 phase, right, and 6 real numbers, and this extra phase theta f. Well, theta f is just argument determinant of these 2 original Y matrices. Okay, this So
why the U1 and U2 terms are not affected? Why the kinetic terms of U2 and U1 terms are not affected?
Kinetic.
Why there is no contribution from kinetic term of U2 and U1?
There is, sorry, you mean the UC? Which U's are you talking about?
I mean
So these are the fields.
The SM is SU3 plus SU2 plus U1.
Right.
The contribution is only from the SU3 term, right?
Correct.
Why not from SU2 or U1 terms?
Why not from?
This SU3 is flavor SU3.
This is between the quarks are being rotated, right? So
It's not the QCD SU3.
Okay, so I'm still missing the part of the question. So are you confused about when I say 3 cross 3 matrices and this is an LU and RU pieces? So this is between 3 different generations, up quark, down quark, etc. So on and so forth. Does that? Okay. Okay. Right. So this part is done. Right. So what I do there, now let us put everything together that we had. We talked about a different kind of a physics generation, that's the flavor physics. Now there is QCD which you are talking about. The fundamental physics, it has the kinetic terms of the gluons, and it has a topological term which looks exactly the same as the operator is there, right? Where the GG dual is the same operator. So originally when I started with this basis, I had a theta s term, and in that basis I had this complicated mess which I have simplified in terms of 3 angles and 1 phase and this theta f piece. But if you see, these two operators looks the same. So if I put it all together, then it looks like, okay, first two terms just go over there, then I just combine these two terms to write as a theta bar piece. Okay, so now the counting is straightforward. There are 3 real numbers, diagonal and real, only from yu and yd. This is an SU3 element which has a 3 angles, 1 phase, and there is an extra phase. Okay, so these are all the observables that remains at the end of the day from the flavor sector. That has the imprint of whatever you have done at higher energy. Okay. All right. Now, at that point, let me scale that theory down to electroweak symmetry breaking. So only thing that does is basically replace that H, which was the Higgs field, by a number, right? 246 GeV by square root of 2 or 174 GeV, right? If I convert it into a number, it immediately becomes the mass terms for the quarks. So for example, this term becomes the mass terms on the up-type quarks. These terms become almost the mass term of the down-type quarks because there is a mass, but there is also this angle, right? If this is confusing you, if you're a standard model, all you need to do is again redefine your D, and you will find this VCKM showing up in the interactions of W between U and D. Okay, but this is the same Lagrangian as over here, and you have this extra phase hanging out. Okay, so if you do now the counting in the standard model, total number of observables we have is actually 2. So there is a phase, as I said, in VCKM. There is a phase that's hanging around over here. So 2 phases that's observable out of the flavor. Okay, and I shouldn't just say this one is flavor, but as I said, this is a combination of the flavor and QCD. Okay, very good. And this is the strong CP problem. So let me just give you the number, but if you are interested in knowing how these numbers come out, then we can, I can work it out on the blackboard and show it to you. So 3 phases, as I said. Theta CKM, there is a theta f which comes from here, which is argument determinant of yu times yd. Origin of it is a flavor, and there is a QCD phase which is theta s, which, as I said, coming from the QCD sector. 3 numbers, but we measure only 2. So weak phase theta CKM, that turns out to be ordered half, and this combination theta bar, which is a linear combination of theta n and theta s, we haven't found it, but we have a limit. It said it has to be less than 10 to the power minus 10. Okay, so, and you see where the problem is, right? Meaning, let's say I'm God and I'm writing my theory of flavor, right? So when I write the theory of flavor, what do I expect? There are 2 phases that I generate at the end of the day. I expect them, if I don't do something really crazy, I'll get them to be of the same order. I'm not talking about the difference of one being 1 and other being 0.1, right? I don't want it something like 10 to the power minus 10, right? So I expect them to be same. If I expect them to be same, I expect theta CKM and theta f to be of the same order. But then to get 10 to the power minus 10, I require my theta s to be minus theta f, minus theta f plus 10 to the power minus 10, right? Something like that, or minus theta f, whatever be that ultimate number that you get. And that is a problematic, because why this number should track this particular number? It makes no sense whatsoever. And that's really the essence of what the strong CP problem is, right? That 2 unrelated things. So first, 2 statements. One statement is that whichever way we are generating flavor, we expect genetically 2 comparable numbers. Okay, unless you do something crazy. We'll talk about it, doing something crazy. Or you have 2 different information coming from 2 different sectors. They are comparable to extreme degree, that order 1 in 10 to the power minus 10 at least. Okay, they should have that information. Okay, so
the 2 spaces that you wrote at the bottom,
Yeah.
so they are the ones that you are basically combining.
Right. These two guys together, theta f plus theta s, that is measured to be 10 to the power minus 10. Okay. So now, as I said, people are creative, and it takes a very, very smart person to come out and give you a flavor model which makes this guy an element of a 3x3 matrix to be non-zero, the determinant to be completely real. Okay. But that's a special kind of model building, but you also have to assume that this theta is to be equal to 0. So that's a beautiful kind of solution, and only very, very smart people can come up with things like that. Extremely original. There are axions and everything else, and this is the context. Okay, so that's the third time I mentioned axion. And part of it, I'll mention it one more time. As you will see that SM actually has, no, I'll not talk about that, but I'll comment. SM actually has an axion, but I'll come to that. But here's the best solution to a problem is actually to show that there is no problem, right? So that you don't have to do any construction. You don't have to worry about anything. No extra degrees of freedom, no extra couplings, no extra, you don't have to be genius to do that. So what is the best solution? Is that you say that there is a limit in which the standard model theta bar is not observable. Okay, so that you don't need any BSM, and that limit is when this guy is 0, that the determinant of yu times yd is 0, right? So that tells you that one of the eigenvalue is 0, right? The way to see that is you realize that, let me come over here. Way to see is you realize that the first basis when we worked out this particular basis, the theta f was in the flavor sector, theta s was in QCD, right? The second basis that I worked out in that particular case, there is, if I call this the flavor sector, there is no theta f, it's entirely which is looking like a QCD. And the difference between them is a quark redefinition. Okay, so if one of the quark is massless, all you do, you redefine the quark such a way that theta s goes away, then it should show up over here. But you remember the determinant is 0. So even if you have introduced a new phase, 0 times that phase still gives you 0. The other way of saying that is, let's say my up-quark is massless, so I have a freedom to rotate it as much as I want. To give whatever phase I do, I will not change this particular factor. So at the end of the day, the entire phase can be absorbed by redefining, let's say, up-quark. Okay. A cleverer way of saying that is, if I go to an arbitrary, if my determinant yu times yd is 0, you can go to an arbitrary basis where the up-quark, for example, is defined from each other by a single phase. In that different basis, this parameter changes, but this remains the same. So it looks like the value of theta bar is a basis dependent, okay, in that particular case. And if it is a basis dependent, then you know it is not an observable. Okay, that's the way to do. Right. Now, is that still logical to think about, right? Well, to check that, first thing you do is open PDG. Nowadays people do Google, but in our times we are not that Google friendly. So we open PDG, and PDG gives you the masses of up-quark, the lightest of them, the down-quark and the strange quark, and you see like you're far, far away. Many hundreds, thousands of sigmas away from 0, right? So naively, this is, this is a bogus solution, especially today. And you need BSM because standard model exactly cannot solve it, right? Period. Okay. But as I said, there are subtleties within subtleties, and strong CP problem is like that. First thing that you see, what are these MU, MD, MS? The values that you see here from PDG, these are what is measured. Okay. Now, the statement here is the measured value of what these things are. This is not just eigenvalues of the Yukawa couplings times Vy square root of 2. Okay. The reason why is such that is because you realize that for U, D and S, these masses are far below the QCD strong coupling scale. Okay. So I never ever, so for charm and bottom and top, which are still away, so they form, the bound states they form is still non-relativistic bound state. Charm not so much, but still bottom is a relativistic bound state. If it's a relativistic bound state, I can still make sense of the asymptotic state that I observed, which is the bound state, much, much closer to the quark degree of freedom. Okay. Again, quark is a field that has a creation and annihilation operator for, so-called quarks, right? This is one particle state. The thing that you observe, remember we're talking about asymmetries, are the so-called asymptotic states, which are not the quarks, right? But at least for non-relativistic bound states, you have some way to connect these. For relativistic bound states like SU and D, there is no such thing. Okay, you literally have to talk about kaons and pions and all the bound states, which are relativistic, right? If you remember, like an up and down, which I said the masses are of the order of MeVs, but the pion mass is of the order of hundreds of MeV, right? So you see that most of their energy is actually not from their masses, it's from QCD, okay? So in any case, so there is a difference between what you measure and the Lagrangian parameter that you write, okay? And that's basically going to be the talk. All right, how are you doing on time? All right, so let me recapitulate. How do I understand, it's very clear that I need to know what the eigenvalues of these things are. These are related to masses of my pions that I measure experimentally and their spectroscopy, okay? But the thing is that I need a way to connect these quark masses, which at the UV looks like this Y times V electroweak, right? And this is the Y that we are after. Some way I need to connect these masses to the pion masses and figure this out, right? And then the measurement and everything would come, okay? So the way to go from there to there is what chi-pt is. Right. So chi-pt provides the connection between the quark masses and the pion masses. The way it works is that the way we understand the low energy dynamics and experimentally probe it is by constructing this chi-pt. From the data, we are very much sure that at the end of the day, you form a vacuum expectation value of this quark and anti-quark, like U times UC, D times DC, and S times SC, for example. Okay, if you form a condensates like that, you spontaneously break the flavor thing that we are talking about, SU3, which are associated with LU matrices, and SU3R, which are associated with R matrices, into the diagonal flavor group, right? So now you know that in spontaneous symmetry breaking, for every symmetry that you break, you get a massless degree of freedom, right? So that's the Nambu-Goldstone boson. Now, what the spectrum therefore is, because if you break into a diagonal SUF times SUF going into an SUF, the spectrum consists of, so there are one single SUF broken, which has the f square minus 1 directions. So for every direction, you get a massless degree of freedom. And that's, so 3 square minus 1, that's 8 Nambu-Goldstone bosons, right? Now, these symmetries were actually not the real symmetry. So now if you turn on the quark masses, it tilts the potential. So what was massless, because of this tilt, gets a little bit of mass. And so these are the pseudo-Goldstone boson. The counting degrees of freedom remains the same, okay? And so this is the 8 Goldstone boson, okay? The way we describe them is pseudo-Goldstone bosons. And the way we describe them is typically using the nonlinear realization, because there are symmetries that allows you to construct the full theory, the chi-pt, order by order, right? You realize that I can no longer, because this is a strongly coupled theory, because in terms of the quarks, it becomes the strongly coupled theory. So I have to write down a theory in terms of the pions, right? There is no straightforward way that I can connect the theory of quark to the theory of pion. I have to go to roundabout way, okay? But what I know, for example, are the symmetries of the ultraviolet and the symmetries of the infrared, okay? Use the symmetries and power counting to find an effective field theory of my degrees of freedom. Okay, order by order in expansion, and that is what chi-pt is. Once I do it, then I can match the UV theory based on the symmetry properties again to my IR theory, and that's how these terms work out. Is that part clear? So UV theory described in terms of the quarks and the parameters of the quark Lagrangian. The low energy theory built using the pion degrees of freedom, in a sense that they create and annihilate these one particle pion states. Okay, we utilize the symmetries to construct the full Lagrangian order by order, the infinite number of terms. Okay, but you construct order by order, and then use the symmetry of the ultraviolet and the symmetry of the infrared to connect. Okay, and that's how you get to connect the ultraviolet parameters with the infrared parameters. Okay, that's how from what you measure, which is the infrared physics, that you can connect it to ultraviolet parameters, which is like the quark masses and mixing and things like that, right? That's the whole story. So the main thing that you learn is that you find one field U, you know how it transforms under R and L, which is again this SU3 matrix of the right-handed guys, L, which is the SU3 matrix of the left-handed guys. Okay, and this U contains all the pions. Now, as I said, quark masses break the chiral symmetry. So one way to do that is we say, well, let us first treat the quark masses as the field that actually also transforms. Okay, and after I do all my entire calculation, I fix all the terms because I am assuming the quark masses are transforming. Then I will set it to numbers. Okay, and then I will get all the exact terms. Okay, is that part clear? Yeah.
So I'm a little confused about why you want to work with the low energy stuff, because
I measure low energy stuff.
But in perturbative QCD, for instance, how do you fix the masses of the quarks that show up in when you say light quarks? So the Lagrangian mass of the quarks and the Lagrangian would be the ones that I expect would be in scattering the quarks, right?
No. Let us be careful about that, because the way, so let's do physical denormalization scheme. So the masses of a fermion that you put in is where the pole is supposed to be.
Right.
So you need to get the piece q square to that level to see where the pole exactly is, right? The asymptotic states are proton, neutron, and the pion. This is what you scatter.
Yeah,
right?
Yeah. So what do people quote when they quote, like for instance the mass of the perturbative mass is that, what are they quoting actually?
I'm coming to it. So I'm just trying to connect, and how I connect, this is what I'm describing. So what you are right is the saying that UV physics, which I wrote right in terms of the quarks and their parameters, like the mass of the quarks. But these are not physical that way, right? Unless until I can connect these to the pions which I observe and their various parameters. Okay, and this process is the process of.
Is it fair to say that somehow you're disagreeing with the perturbatively coated masses of quarks?
This is not perturbatively coated mass.
What are they?
This is the process via which we determine what these masses are.
So if perturbative QCD, what would
so okay,
the mass of the quark?
yeah. So this, let me say this way: these masses are what you need to put in, for example, in MS bar scheme, so that according to them, the pion spectra would look right. So the pion spectra.
But isn't there a notion of perturbative QCD mass of quarks? That's what I'm.
No,
I think
there's no such thing.
No, below lambda QCD, there is no perturbative QCD.
Right. Below lambda QCD is fine. But
Yeah.
I'm saying when you say that the masses of perturbative quarks.
So in none of your calculation, if your p square above a GeV, none of your calculation is affected by your half MeV mass of a down quark.
Sure, I agree. I'm just saying that these masses, then how should I think of them? I should think of them as the dressed masses? Is that how I should think of them in some sense?
These masses are what you need to have in MS bar scheme put in, so that after matching they would give you the right pion masses and the scattering element.
These come from the lattice measurements in some sense.
Some of them come, but some of them you have to get the out of the pion, and but lattice doesn't get them. That's the, let me.
Nowadays that is.
No. That's the whole talk is about this. So just hold your horse. Yeah. So it is it is subtle. Meaning in terms of lattice, you measure number, What you get is numbers, right, at the end of the day. And then there are various S matrices you write in your theory. What you can do using lattice is match the chi-pt calculations in various different ways, and from that you get this number, and from that you need chi-pt. And the way you fix the different values is by various lattice numbers, right? So just to cut that story short, as I'll show you that there are straightforward pieces that you will capture it over here in chi-pt that will come directly from naive or straightforward, shouldn't say naive, still complicated, lattice QCD. But there are pieces into that same pion Lagrangian which are topological in nature, will not come directly from lattice. To simulate them, you need to go to the next level. Okay?
So what is the, what you stated about the mass here, I think I understand, which is basically what you're saying is that in MS bar, you need this in order to reproduce the pion mass.
Yes.
So that I think I understand. But then what is the connection between what people sometimes call rust masses versus, the free gas, mass or whatever?
There are, look, I mean, there are various different, I don't think there is a straightforward definition that way. Because, I mean, often we confuse between English language and a semi-quantum description of things, but, let's stick to...
No, but I think the point is that I would not think that this would be the natural thing that you would have in the Lagrange. This is like, I agree that this is what you should get in MS bar in order to get the pion mass, that I agree.
Okay.
And I think that's a completely well-defined definition. But I
See,
don't know whether
look. Perturbative or non-perturbative, Lagrangian parameters are all scheme dependent.
Sure.
Right? Only in physical renormalization scheme that you actually put the poles into the parameters. Yeah. Right? That's the special scheme. Yeah. But that's useless scheme because you can't calculate in this scheme.
Right, but I mean then what is but the alternative that you're proposing, it doesn't seem like that is the...
No, I'm not proposing anything new.
Okay.
I'm just telling you what the state of art is right now. Right? I haven't gone to that level. A lot of us do many things without understanding details. Right? Right? So when we see those things, when I have done these things in my grad school, right, I would simply take them, even let's say a year before, I would simply take them and put it over here. I will use that as an equality, right? But 1 year after today, I'm hesitant to do that because I learned little bit epsilon, little bit more. Okay? It's okay. All right. Right. So the main thing what I trying to say is that the low energy theory is described in terms of two fields. There's a U matrix and there's a chi matrix, which is basically the mass matrices if you think of it. And just think of it, it has a very specific transformation property under the L and R. Okay? These are the two ingredient, and to large extent I'd be able to calculate order by order what my chiral Lagrangian is. Right. So just to scare you, if I have that, the leading order term that you're going to write looks like that, d mu dagger d mu, which is naive. Then is a chi dagger u, chi dagger u. That's the lowest dimensional operator that you can write. Okay. Then higher order term, which is P4 Lagrangian, people have walked through this and you can classify and you realize that there are 8 different operators. For example, you take this operator, square it. Take this operator, square it, somewhere combinations of that. Multiply this with this. Product of it's a double trace, or you multiply the operator themselves and then trace, right? Like that. So you can play this game and there are 8 different operators and that comes in the next order. The way to realize the power counting works is there are momentum. So these are p square. Okay. So for every p square there is a lambda. Every p there is a lambda. Lambda is higher than p. So I'm doing it low energy. Okay. High energy, I told it my cutoff to be 770 MeV. Okay, so that as long as my P is lower than 770 MeV, the energy is lower than 770 MeV, there's a P square by lambda square gives me a very good control over order by order correction. Okay, so that's how we construct this. So P4 Lagrangian, which is more suppressed, as I said, there are 8 different operators. Right. Now let's make our life easier. Let's do the leading order Lagrangian. When you expand this guy, you get the pion mass. So U contains the pi, it's e to the power pi. So when you expand e to the power pi, you get a polynomial, right? So you get a cosine pi basically, and that cosine pi gives you pi square as one of the terms. And you can see it because the chi has a quark masses built into that, mu, md and ms. So you see that directly there's a pion mass is related to the quark mass. It absolutely makes sense because if you take the quark masses to 0, it looks like m pi squared to 0. This is what I talked about, right? If quark masses are not there, then you have a Nambu-Goldstone bosons, which gives you a flat potential. You put in quark masses, distill the potential, and that gives you the masses of the pion, right? So amount of mass must be proportional to mu plus md. Great. So you got a very, very consistent result, right? So in exactly the same manner, I could be happy here. So that's to answer the question. If I can measure the spectroscopy at this order, if I have sufficient information, I can determine what my mu and md is. Okay? Good. So, but as I said, yeah.
So just in the same spirit, for the kaon mass,
Yeah.
if I turn off the u or the d,
Yes.
does it lattice the kaon mass also go down proportionally?
In lattice, you can't take mu and md to 0. Right? They are even having a hard time to get to the, like what the pole masses are, but you can do it right now. But you do get, you reproduce, I mean, that is a consistency check for lattice.
Yeah, that's right.
They have to go to 0. Right? The way to understand is, the other way to give you a little technical answer is what sort of renormalization have you put in for the quark masses. If it's a productive renormalization, the way you think in weakly coupled field theory, that the quark masses or the fermion masses only gets renormalized in a multiplicative way, right? Then you get a different story, but that's not actually completely right. So there you have to add something more, and that's where the other pieces comes in. Okay. As I said, things are far more nuanced. So as I said, I had two parameters, right? The mass parameter, and it has a specific transformation property. Now you could look at it and you can define a new parameter, determinant of this chi divided by chi. This is called the cofactor of chi. This particular matrix has again the identical structure, identical symmetry transformation. So it's a new spurion, right? And it's also goes well smoothly to 0. Okay, so it's a perfectly valid spurion, just like what chi is, right? So when we are drawing with writing all possible operators, it looks to me a completely valid spurion as well, right? So I should include that, right? But again, since it has all the transformation as a chi dagger, it turns out if I transform chi by a cofactor of chi dagger, which has, again, cofactor of chi dagger has all the symmetry transformation property of chi, you can't distinguish them. So Lagrangian chi goes to Lagrangian chi plus a cofactor chi. Okay, this is extremely subtle observation, because this tells you that if these two Lagrangian are actually equal, then there is a redundancy. Okay. In fact, this turns out to be equal, and that you can show them by using the Cayley-Hamiltonian and so on and so forth. But where this comes out is that when you add this cofactor term, that extra pieces that comes out, as you shift this chi by this cofactor, the extra pieces that you add looks exactly like the terms in your higher order piece, P4 Lagrangian.
What was the chi, sorry?
Chi was basically the mass matrix. Think of it just like a mass matrix multiplied by a number. Okay, so the main point is that it looks like there is a redundancy in terms of, if I shift my chi by this amount, all the other terms in my Lagrangian in P4 changes, but on the other hand, if I shift the coefficient also at the same time, there is a complete redundancy. Okay, and this is observation long time back. That's called the Kaplan-Manohar gauge transformation. Okay, now this is a very deep thing in terms of it basically connects you the leading order P square Lagrangian with the next to leading order P4 Lagrangian pieces. Okay, so if you want to make the statement, as we said, the pion masses are related to up and down type quark masses, that statement right now looks to me, whether you are doing it at LO or you're doing it at LO, it's slightly different. Okay, now at LO, as I said, it's straightforward. If I now try to use an LO, naively, if I just write down, then the mass is like the pion mass, looks like this is from the leading order, as I said, is proportional to mu plus md, but then it's also proportional to mu plus md times ms that comes from the next order term. Okay, I don't do any transformation, I just take the original Lagrangian, P4 Lagrangian, this is the term from the next guy. Okay, but now I can utilize the fact that I can shift my chi by this guy, and then corresponding my L6 and L6 and L7 I can shift, then I can dump everything in terms of shift the fields or the masses so that the same pi square looks like it's given in terms of only the leading order formula. Okay, and that is utter confusion. In terms of, it looks like whatever your bases are, right? Then it becomes the question, what your bases are, what you are extracting is completely basis dependent. Okay, and that was the conclusion. That was a conclusion made in '86 by Kaplan and Manohar, showing that you can't really extract them beyond a certain amount of confusion. Okay, the same observation repeated in '94 by Tom Banks, E.O.C. Neer, and Seibert. Okay. But that's the story. Okay, that's the story. Right. So I can't. Now we remember in this basis, as I said, I haven't done any of this transformation. So if I have my flavor high scale YU and YD that got changed to MU and MD, and I'm curious that to know whether my MU is 0 or not. Right. That is the question I'm after. But it looks like I can only measure up to a point. I cannot figure out what is the true MU and MD is. Right? But it turns out that yes, I can't figure out what true MU and MD is, but I can check my hypothesis whether my MU is 0 or not. Right? If you take this guy and you take your MU to 0, then you can show that the parameter that you get in this second guy, where only the leading order remains, is connected to mu u by mu d, is connected to mu s, which again you extracted from the data using leading order term via some beta 2 by beta 1 parameter. Okay, so first of all, what it tells me, if you have Lagrangian parameter mu equal to 0 or yu equal to 0, okay, that particular case you still will have massive pions, period. Okay, you will have massive pions, you will generate pions, and it depends on the value of this beta 2 by beta 1 is, which is related to this L6 minus L7. This is LEC's low energy constant, what these low energy constants are. So if God tells me what these low energy constants are, I can immediately tell you what is the, even if I take mu equal to 0, what would be the effective measured value of mu is going to be. Okay. So if you put down here mu e equals to 2 MeV, mu d equals to 5 MeV, this combination has to be order of 5 by GeV. Right? Okay. So this is the part of the story. But then I should simply go and derive this guy. It turns out I can't derive it. I can look at the data. I use chi-pt, I use the data, and I just fit. Okay? We can do that, and we do that, but we don't like it much, right? The reason is that when we calculate these things, we also take the large n things, because we love large n. It gives you a very, very large n, means that for the color n equals to 3, we take the large n limit, and that somewhat tells you, simplifies the math, gives you a lot of intuition, and that tells you that some of the parameters like L6 and L4, these are small. Okay, because these are n suppressed. Right? So large n actually tells us that these are small, beta 2 by beta 1 can never be this large, and the generated mu u, if you start with mu equal to 0, always is small. Okay? We can extract it from the fitting data, but there also I will show you that large n plays a big role. Okay? Now we come to lattice, but here was the point about it. Some of the effects, so chi-pt describes has all the effect. Okay, a lot of the effect at the end of the day is topological in nature, and this is what lattice has really hard time simulating. Okay, there is one paper. There is a single paper that calculated, but when I talk to our lattice guys, let's say it's still very, very early day to estimate whether or not you can calculate the topological effect of a lattice box unless you utilize manifest chirality in a finite box, which people don't do. That tells you you have to utilize certain specific fermions, overlap fermions, which is very expensive, still far away from it. Okay, right. And this is what I meant by fitting. So here is, for example, this is the one that everyone quotes, 2014, utilizing the data. You fit with the data and you come with no preconception. What you realize that your L4 and L6, which large n tells you are supposed to be small, turns out actually comparable to all the other big numbers. Okay, so people see that and then say, okay, this must be wrong because large n tells us these numbers are small. Okay, so then what you do, typically people do, is that they constrain these numbers like L4 to be small and then they fit the rest. And the final number that people typically quote what beta 2 by beta 1 is from these fits, for example, where you set it to 0, these L4 and L6, and then you give the rest of the number, right? And from that you conclude, oh, okay, my pion masses are too small to be coming out of, massless up-quark. Okay, that's the story.
So when you say fit, what does they fit to actually? The current fit low energy constraints?
Yeah. I think this is the same. They utilize, they set some of those parameters to be small because it's the same fit at the end of the day.
But just set these two parameters.
Yeah, so you have both of them. That's a nice table for us too, because side by side you could see. Now if you actually utilize naively this, you actually get beta 2 by beta 1 is order 6. Okay.
Just n equals 3, right? You're using n equals 3.
Yeah, so when we utilize this, like how the different LECs look like, you find some of the LECs goes as n to the power 0, some of them goes as n squared and things like that. So we imagine that this would hold true even for n equals to 3, because many of these we have seen in the data, large n intuition. What?
Estimate the numbers you put in n equals 3. Like
Yeah, at the end of the day, this is what you do, but you neglect terms. Like for example, ordered n terms you neglect and then you put values and seem to fit reasonably well. Okay, so I don't know how far we'll go because we're out of the talk. This is where the technical talk starts. But as I said, if you can come up to this point, you can appreciate what the subtleties of strong CP is, how convoluted the story is. I think that's quite a lot. So this part I'll go fast, but let me give it 2 minutes on what the global picture of what this buzzword typically mean. So this is the full story of how you think about things. So this is the QCD Lagrangian what I talked about. This is where God encodes all the knowledge. Observables are color neutral bound states of mesons and baryons. Okay, the way you connect them, you use effective field theories like IPTs, NRQCDs, etc. You also have lattice that that takes information, gives information, fits many things together, and that's how you get a beautiful picture between them. In between you have generic tools, right? Generic tools like QCD, some rules, large n limits of QCD that allows you, let's say, bypass lattice to certain extent, effective field theories to certain extent, but it also allows you to come from here to talk about the color neutral, bound state and stuff like that. Okay, so this buzzword, this thing is a particular limit of QCD. I'll come to that, what this limit is. So when I started thinking about it, the authors more or less were concerned about how to connect this guy with that guy, right? In theory space, this venture is in the theory space. So part of the stuff that I thought about was, well, screw this part, I don't want to care about this. But let's say this is a theory which is completely calculable. Forget how I can go from here to there. It's calculable. You calculate and look at various things. From that, you see how similar this, what we observe and what we get from this particular theory. Okay, and it turns out you learn a lot. You learn various scaling limits, folds, everything, etc. As I said, if you ever have time, so the first one that we wrote is actually to figure out what the dynamics of eta prime is. Learning from this, eta prime is one of the hardest thing to calculate because of the anomalies and stuff. So it's actually a nice paper to talk about it. Okay, now what is this buzzword typically means? The buzzword is you take your QCD, you add a little bit of SQCD in it, the supersymmetry in it, make it fully supersymmetric QCD. Now the beautiful part of this theory is exact. In terms of a perturbative or non-perturbative, you actually know what the potential looks like at the end of the day. Okay, you know it because Cyberg said so. Okay. And you take that particular theory and then you add a little bit of SUSY breaking. Okay, as you add a little bit of SUSY breaking, you start deforming the particle from the superpartners spectra. Okay, you go to a limit where it is still deformed and you figure out various scalings from that. And then you intuit that some of the scalings will hold. Even if I can't take it away, make as big a difference between particle and the superpartners, but the things that I learned, we hope that some of it lessons comes in the QCD itself. Okay, that's a different way of looking at it, and that's the eta prime was the result of that. Okay, so half second I will just derive. It's an SU3 fully supersymmetric quark, anti-quark, UV, IR in terms of QCD singlets, which are the mesons, okay, composite operator. Then Cyberg says, well, no, Affleck and Tuhin, and Cyberg says, well, no, I also know what the potential looks like. Since I know the M matrix of mesons, the potential looks like in a very this weird format, it comes out to 1 over determinant M to the power some n minus f, okay. The lambda is basically the strong coupling scale. Okay, so they had this whole program. This is called typically Cybergology. In a sense, for different values of flavor for a given number of color, they chalked out how the whole phase space looks like. Still good, but this is not QCD. This is SQCD. Okay, so you need to create a gap between particle and superpartner. But if you want to do it, it's actually hard because the way you are creating gap, that turns out having a bigger effect on the spectrum than creating gap itself. Okay, that's very hard. It depends on how SUSY breaking is communicated, depends from all scales of UV, IR, and so on and so forth. It turns out there's a specific way that comes as a savior that's called anomaly mediated SUSY breaking. Okay, it's a pure supergravity way of how you break SUSY. Again, people discussed it in 98, 99, 2000, and whole part of 2010, where people are still thinking of supersymmetry as a candidate for beyond the standard model physics. So there, the gaps that they were looking at, order TV gap, right? That is what people wanted, superpartner to come, and that was an elegant way to get there. Okay, so that's that most of our knowledge comes from all the studies over there. But we don't want to create a gap. We want a small gap, order lambda QCD. Learn about the theory, forget about the rest. Okay, right. So this is the structure. Forget everything else except that for every field, there's a super field you write together where the particle and superpartner are all together. And this field phi is a special field. It's a supergravity field, and this M is what is parameterizing the SUSY breaking, right? It has to do with the gravity no mass. Lot of math, you do a lot of math. The main part again, as you perturb it, again, as I said, before you do perturbation, before I have a full SQCD, I know what the potential looks like. Then I perturb it a little bit by including this mass parameter, then I actually also know what the full superpotential looks like, okay? You can take it, let's say for n greater than f, n equal to f, you then try to figure out from the meson matrix how I'm going to get the pion. You use a specific normalization where the linear modes are in S, the pion modes are in U. You integrate out the linear modes and you derive the chi-pt. That's it. A lot of maths, few months of maths, maybe more. But after that, once you do this, start with exact potential, break up the fields in terms of linear modes and the pion modes which you want, integrate out properly, and you find your chi-pt of your pions. Okay. Now when I said that I find my chi-pt of my pion, that means I actually know all the operators and I know what the coefficients are. So all the LECs, which were parameters, which either lattice was going to come and fix it, which I actually derive it over here. Okay. Now the main thing to understand from here, the way we derive it over here, this includes the effect of the linear modes. Okay. It only includes the effect of the linear mode. It does not include the effect of the superpartners. So now you can take the limit of the superpartners. The effect of the superpartners just decouple, because all of their effect are their mass suppressed.
What are you integrating here exactly?
The linear mode, for example, in our case, would be the scalar modes of the corresponding pion fields.
Okay.
Right.
Okay.
So that effect is fully captured.
Okay.
Okay, and that is what we are capturing over here. And chi-pt comes mostly from the vector modes integration and the scalar mode integration. Right. So we do not reproduce. We do not find the operators that you get by integrating out rho, for example, but we find all the operators that comes out of that, and you get the right end scaling and everything. Okay. So I derive my chi-pt. So that's the main thing.
What sets the order by order?
Because S and H, this is the quark mass parameter that sets the masses of these, and that you integrate out. So I solve it exactly for, let's say, MQ equal to 0, quark mass to be equal to 0. Then, because otherwise it becomes harder to solve, and then I treat MQ as a perturbing parameter, and then I find my chi-pt just like other, right? I mean MQ over lambda.
Right. Exactly.
Right. Okay. Great. So as I said, I can derive this parameter now. Once I derive this parameter, I find that if I take the theory where n is greater than f, it looks like it's very, very small. If n is equal to f, this looks like 0.1 times phi. If you remember, you want this number to be around 0.5. Okay. So main thing is that you get a large value of the predicted or measured up-type mass. Okay, even if you set the Yukawa generated mu to be equal to 0. Okay, and then some of them intriguing stuff is that if you take n greater than f and you take n scaling, you realize that some of them, all of them are scaling exactly like they should be, as in QCD and in chi-pt. And the intuition works in terms of which one should be larger, which one should be smaller. However, if you take the f equal to n theory, all of this go away. If f and n are comparable, then all these large n arguments simply break down in this QCD-like theory. Okay, here is the conclusion. So NMSBPSK it's a limit of QCD. It's not QCD, but it's a fully calculable theory. And what our intuition is that it gives you some understanding of what QCD is. Okay, spectra and phenomenology, it mimics that. In QCD we have non-trivial results of eta prime physics. Like some of it we realize there has been from Witten to there's many arguments about how much the instanton generates eta prime potentials and stuff, like how in large n it works. Some of them we can understand and we can realize and have non-trivial things we can point out using this language. We found large LECs in f equal to n case that does not conform to large n expectations. Okay, and if you actually take our result and you naively extrapolate to QCD, then there is no strong CP problem. And I don't care about that, because at the end of the day, but what I care about is this. Something that whenever we are thinking of extracting from data, for example, it is supposed to be precious, and this is where our intuition does play a lot of role. And I think we need to recheck our intuition when f equals to n. It's not, so quantitatively when you say n equal to 3, the correction is 30% or so. I'm not talking about quantitative stuff. I was talking about f equal to n. Whether it's actually because the large n is derived when you fix f, take n, right? That's it, right? So and that's what people use. But this is actually f equal to n. Like some of the branches on eta prime potential we found to be, it's going as n minus f, not n minus f branches, as opposed to what Wheaton claimed is it should go as n branches. And so that's the part, and that's basically the summary of everything. Again, I went pretty fast about the technical things. As I said, if you care, let me know, then I will entertain you. Thank you.
What happens to B0 in this SUSY derived chiral PP?
We utilize all of those, no?
No, B0, what does it lead to? Meaning, what does it correspond to, say, the scale of what in the SUSY procedure?
I have to check. I don't remember the exact number.
Because it's a mass,
It's a mass parameter.
Yes, mass parameter.
Yeah, it's related to lambda at the end of the day, right?
That's right.
That's we get. I'll just check, double check. 1 second. Actually, I have all the expressions. I can show you this somewhere.
And it has nothing to do with SUSY breaking or anything.
So you see that?
Okay.
So depends on what regime are you looking at and things like that. So when we say m, this is in a case where m is smaller than lambda QCD. If you take m is the SUSY breaking piece. If you take larger than lambda QCD, that gets replaced by lambda QCD. Things like that. I mean, we take the limit also. Assuming that analytically you can go, you go, and we don't see any reason why you can't. Well, you need to stop.
So is the f equal to n theory confining in the infer?
So yeah, it confines, but it has this quantum moduli space, right? And so that is, I think I mentioned it somewhere. In the presence of this AMSB twist. So when I'm saying f equal to n theory, what I mean f equal to not the original Cyborg, f equal to n with this f equal to n. So this gives you the, where is this? So this is the M matrix. So determinant M is equal to BB bar. That's the classical constraint. So quantum modified constraint is determinant of M minus BB bar is equal to lambda to the power n, right? So the way we implemented this is basically utilizing that, you have to be on the track of the quantum moduli space, right? So there we had this Lagrange parameter, that's how we implemented in superpotential, that Lagrange parameter that sets this to be equal to.
That guy is kind of like the thing that it's basically the studio.
Yeah, there is a better interpretation of it. I take f equals to n plus 1, which is S confining, everything is fine, and then I take one flavor out, this turns out to be that flavor in that. So f equal to n plus 1 to f equal to n.
If you increase the number of supersymmetries, maybe better, right?
But that's not nature.
Okay.
You don't have this kind of potential.
But it is going to do anything.
Even n equal to 1, right? It's a struggle, right? So in that sense, you would say n equal to 2, you already solved confinement, right? There's no point, but we haven't, because it really has nothing to do with nature. In fact, all the phases that we have in SUN has nothing to do with our QCD. But the moment you have this AMSB, somehow it looks like the IR sort of looks like QCD-like. It has chiral symmetry breaking, it has confinement, and it has all the nice features that you would like to have.
So I'll ask the same question that I basically had earlier. So I would think that the natural way to define, so essentially it looks like the question is to define this Lagrangian parameters in a useful operational way. Is that a fair statement?
No, see, this is,
your argument was based on a path integral argument, right? The measure changes, And then the
That's for the theta bar parameter.
Sure, yeah.
Right, and that is where all the problems and redefinition comes in.
Right. So
now, generic question in QCD for the light quark, how do you define the Lagrangian parameter?
That's exactly what I was asking.
Right,
Yeah.
and I don't think there is any good way. I mean,
I think lattice is really the only way. That's what I would say.
yes, but except that part is that you also have to be careful about lattice, whether you're simulating all the effects of nature or not.
Yeah.
Right, but yes, that.
So
But you know, I mean, the lattice also give you the MS bar parameters at the end of the day, right? Because there is a connection between the masses that you set in, for which what it corresponds to in the Lagrangian, and then you just fit, right? It's a fit at the end of the day. You fit the all the values so that it looks like nature, and correspondingly what initial parameter that you have taken, right?
yeah,
That's
so,
it.
I mean, yeah, I think the thing I find a little weird is that, like, you know, the quarks you'll never be able to really think of as poles in the S matrix.
Absolutely not.
That you
Yeah.
cannot.
Yeah.
So somehow this is reverse engineering from the mesons to get this mass. So that this feels. I mean, okay. I mean, we can, you know, yeah, but
Right.
I think we understand each other.
Right, but yeah, exactly. But see, at the end of the day, let's say if you care about the strong CP, all you would like to know whether my YU11 is 0 or not, because that has something to do with non-trivial stuff, right? And this is where the subtlety come in. How do I measure this YU11 from what we observe?
Yeah, no.
In between everything is theoretical niceties, but does not have much significance. I mean, ultimately this is what we want, right? Get that parameter out of low energy observables we have. Because you remember, I mean, how do I determine things in a numerical simulation, right? I have measurements on one side out of the black box. There are input parameters that black box acts on, gives me some output observable values, right? Then I keep changing the input parameters so that the output observed values become equal to what I measure, and that tells me what.
Fine. So the point is that when we are starting with MS bar, it somehow feels to me like somehow it's perturbation theory.
Yeah.
It's that there is an element of that.
Right, but well, QCD runs, right? I mean, yeah. So I mean, there's when you talk about generating flavor, this is where QCD is weakly coupled, and you have to think of weak coupling fields. You can't talk about.
But I think what you said about like the fact that the lattice also feeds back in the MS bar is also true. So
Yeah. So there is a crosstalk everywhere. So it's fine. Like if you ask me, like for example, even for top, right? Or how do I measure top mass? So if you go to an experiment, what they actually measure is actually not a mass that you put in your Lagrangian. It's a simulation mass that they measure. It's called kinetic mass, in the Pythia mass, whichever way you want to say it. You vary this, again a black box, you vary this input parameter such that the distribution that you get is equal to the distribution that you observe. Okay, that gives you best fit the kinetic mass or the Pythia mass or something. From that, you go back and you see what is the MS bar mass. That, I mean, you have to have that path even for weakly coupled things. There's a disconnect between what you observe and what we write. But if you have learned one thing, that Lagrangian parameters mean nothing, that would be a success for my. Okay. Anything else? Or?
The scalar part would be tachyonic,
No.
and the MSB. Need not be, right.
No, it's asymptotically free.
Right. No, I'm.
No, so don't think of it, it's a BSMification of the QCD. No, it's not. It's a calculational tool to get the standard model result, right?
Any further questions? Okay, let's thank. Right, because this is a meson fields, essentially.
Huh?
The MSB of the meson fields, right? Essentially.
MSB of the meson field, right. So, I mean, if you think there are multiple issues, like if you think, like for example, the waves